Hello, my name is Bhavik Bakshi, and I'm a professor of chemical and biomolecular engineering here at Ohio State. And what I'm going to be focusing on is assessing sustainability of this complex network that we are dealing with in this DRFEWS project. Essentially, the goal is to assess the implications of the modeling results that we will get in this work in terms of its sustainability implications to the regional economy and ecosystem. So in this presentation, what I'm going to do is begin with first a brief discussion of sustainability concepts, their strengths and weaknesses, various methods for assessing them, and then describe to you what are the things that we are planning to do in this DRFEWS project. So the Brundtland Commission defined sustainability as meeting the needs of the present without compromising the ability of future generations to meet their own needs. This definition would be satisfied by pretty much any arrangement that succeeds in maintaining welfare, that is human well-being, for the indefinite future. In principle, this goal of sustaining welfare can be met if saving and investment compensate for natural resource depletion, technology keeps pace with population growth, and we allow great scope for substitution in production and consumption. Life will be different in the future, but if welfare is maintained, it will at least be as satisfying. All of the ifs that were just mentioned really matter. The idea that sustainability is about sustaining welfare places a lot of faith in technology, substitutability of capital for natural resources, and the ability of markets to transmit the right incentives. Welfare sustainability accounts have been developed. For example, as you can see on this slide, the World Bank's adjusted net savings shown in the bottom line accounts for whether capital is being accumulated at a rate that compensates for depletion of natural resources. You can see that this ANS line includes things like raw material depletion, pollution, and atmospheric carbon dioxide as negatives, and education investment as positive. So ANS is more volatile and does not necessarily rise as GDP and gross savings rise, as you can see in the slide. For the US between 1990 and 2015, in fact, it's difficult to see any upward trend in ANS at all, even when GDP and gross savings have continued to increase. ANS, and indeed the idea of welfare itself, are highly aggregated, and the links between them and actions on the ground are not very well developed. So for sustaining natural resources, there are other approaches that we could utilize other than this purely aggregated type of metric that we've been talking about so far. Because we do need to sustain specific resources. Often some resources are critical for human welfare, for example, availability of fresh water. In these cases, prudence would suggest conservation of these resources. Some resources might be valued for their own sake, reflecting motivations beyond human welfare. These arguments suggest a commitment to compensate for depletion of exhaustible resources by augmenting natural resources, to limit the use of renewable resources to a sustainable level, and to sustain some natural entities that are valued highly. Keeping track of this kind of sustainability would require as many separate accounts as there are particular resources subject to sustainability criteria. But the links to on-the-ground actions will be clearer because sustainability alerts would apply to particular resources. However, such an approach is likely to require a lot of data and a lot of monitoring. So perhaps a middle ground is a reasonable business as usual goal, but there is more than enough uncertainty about future prospects to justify some additional prudence. For example, sustaining welfare subject to sustainability constraints for critical natural resources could be one approach. In this case, policy would rely on markets supported by public actions that pass a benefit cost test for business as usual resource allocation decisions, but invoke sustainability constraints when crises loom regarding particular natural resources. Alternatively, we could sustain welfare but with strong risk aversion. In this case, uncertainty can be addressed by incorporating strong risk aversion into the optimization objective of the model. Various empirical tools and applications are available that would be relevant to these kinds of efforts. One that comes from environmental economics is non-market valuation, especially valuation of ecosystem services. And this is an important component of analyses in support of policies that are aimed at sustaining welfare. Another tool and approach that comes more from engineering is called life cycle assessment, and it tracks the production and consumption processes from raw materials through the end-of-life disposal. LCA is typically applied to a given product and associated processes. It aims to reduce the chance of burden shifting along the life cycle, but this requires getting the boundaries right. If the boundaries are too small, the problems will shift outside. If the boundaries are too large, the problem could become intractable. This approach also considers all processes from cradle to grave. It compares alternatives in physical units, unlike monetary units that are preferred in economics. It can track ecosystem services as inputs and outputs of the processes under assessment, again in physical units. But it does not account for aggregate impacts on supply, demand, and value at the scale of the economy. In this DRFEWS project, what we will do is apply the various welfare sustainability criteria that I've talked about, which will aggregate market and non-market goods, for example, ecosystem services, and track them through multi-generational time. We will monitor some specific natural resources, for example, the health of streams and lakes and the quality of fresh water. Apply life cycle assessment methods to key economic sectors to get more of a biophysical insight into them to prevent burden shifting. We will seek to develop cross-scale linkages, for example, between LCA and welfare sustainability. We will experiment with welfare sustainability criteria subject to sustainability constraints for critical resources. And finally, we will experiment explicitly with risk-averse optimization criteria. For example, prioritizing the avoidance of really bad sustainability outcomes in addition to sustaining expected welfare. Thank you.